In this section, we are going to study the colligative properties of solutions. Colligative properties are the properties that depend only on the amount of substance in solution, not their identity. And these include the boiling point, the melting point, freezing point, the vapor pressure, and the osmotic pressure. The relative stability of solid, liquid, and gas phase can be studied by plotting their chemical potential as a function of temperature. In Chapter 3, we learned the fundamental equation, and that is dG equals negative SdT plus VdP, which tells us how Gibbs energy change as temperature pressure change. Now, if we divide by number of moles, we get chemical potential change is negative molar entropy dt plus molar volume dP. For temperature dependence, we look at negative S times dt. That tells us that the chemical potential change with temperature is determined by negative entropy. Negative sign indicates the slope is negative. So if we plot chemical potential as function of temperature, we have a negative slope for all three states, solid, liquid, and the gas phase. Now, gas phase has the highest entropy because it has the most freedom of move. All right, and the solid has the lowest chemical potential, the least freedom of move, and therefore the solid has least entropy, and liquid is in between, and therefore the gas phase chemical potential slope is the largest, and the solid is the smallest, and in between is the liquid. So from this diagram, we see that at a very low temperature, and solid phase has the lowest chemical potential. Okay, now lowest chemical potential means the most stable phase, and that tells us at the lowest temperature, solid is the most stable phase. When you increase temperature, at some point, the slope changes, becomes liquid phase. So liquid phase becomes the lowest chemical potential, and liquid is the most stable phase. When temperature increases enough, a gas phase becomes the lowest chemical potential, and therefore gas phase becomes the most stable phase. So we see that the temperature to change the slope between solid and liquid is the melting point, and the temperature to change the slope between liquid and the gas phase is the boiling point. Now this is for pure substance. Okay, what happens if we add impurity into the solution? Okay, so in last section we learned that when we add impurity, the chemical potential of a mixture, okay, that's the solvent chemical potential in the mixture, all right, should equals to the chemical potential of solvent when it's pure, plus RT ln XA. XA is the mole fraction of the solvent in the mixture, all right. Now, because XA must be less than 1, it's the mole fraction, so maximum is 1, and therefore ln XA must be less than 0. So RTXA is less than 0. Okay, that indicates that chemical potential of A, or the solvent, in the solution must be less than the chemical potential of the solvent when it's pure. So for example, for this equation, 5 equals 6 minus 1, because RT ln XA is negative, so you minus 1, and that indicates 5 is less than 6. So the chemical potential of the solution A in the solution must less than the chemical potential of A when it's pure. And that tells us that whenever you add impurity into a solvent, the chemical potential of the solvent must decrease compared to the pure solvent. All right, so from this discussion, we know that this liquid line must move down because chemical potential decrease when you add impurity. So it goes down, and that brings the the melting point decrease and the new boiling point increase. All right, and that's the two of the colligative properties we are going to discuss: the melting point or freezing point decrease and the boiling point increase. The increase, the amount of increase depends on the concentration of the impurity. So we are going to introduce the equation in the next slide. In the last slide, we showed that when impurity is added to a pure substance, the solvent, the freezing point will decrease and the boiling point will increase. And let's skip all the mathematics, but just give you the conclusion is that the change of the temperature, the freezing point decrease is proportional to the impurity concentration in the solution. This concentration can be either mole fraction or the molality. Okay, note that in these two equations, the left side is the freezing point of the solvent, and on the right side, the concentration is for the impurity. So the change of the temperature, the freezing point temperature for the solvent, is determined by how much impurity you added into it. And so it's amount of impurity, not the identity. It doesn't matter what kind of impurity you add to it. It's the concentration that determines the temperature change. And this is an example of colligative property. Similarly, the boiling point increase for the solvent is proportional by how much impurity you added into it, either mole fraction or molality. Here shows freezing point and boiling point constant for some molecules. For example, water has a freezing point constant 1.86 and a boiling point constant 0.51. Another colligative property is osmotic pressure. So here we show a beaker contains a pure solvent. And inside the solvent, there is a flask contains the same solvent, but with some impurity, so which is labeled as a solution. These two liquids are separated by a membrane which can allow the solvent to go through. Now, from previous discussion, we know that whenever a impurity is added to a solvent, the chemical potential will decrease. So that means the chemical potential of the pure solvent outside the flask is greater than the chemical potential inside the flask. The consequence is that the solvent, pure solvent outside the flask goes into the flask and increase the height of the solution. And this causes a pressure build up. The diffusion ceases until a certain pressure we call pi is reached. And this pressure is called osmotic pressure. Notice that the existence of this osmotic pressure is due to the impurity. Imagine inside the flask, the solvent has no impurity. So inside, outside are the same solvent with no impurity, and the chemical potential are the same. There's no pressure, okay, no solvent diffusion, and therefore no pressure will build up. So this shows that the reason to have this osmotic pressure is because of the impurity. And next we're going to show you the osmotic pressure is proportional to the impurity concentration in the solution. In the last slide, we show that when a pure solvent and an impure solvent or a solution is separated by a membrane, the molecules of the pure solvent will diffuse into the solution, increase the pressure inside the solution, which is called osmotic pressure. The driving force of this diffusion is due to the chemical potential difference. The chemical potential of the pure solvent outside the flask is mu A star. Okay, star means it's pure solvent. And the chemical potential inside the solution equals mu A star plus RT ln XA. So XA is the mole fraction of the solvent. This equation can be modified to mu A, okay, chemical potential of A in the solution minus chemical potential of A when it's pure equals RT ln XA. The left side actually means the chemical potential difference, okay, of the solvent inside the solution, inside the flask and outside flask, because this pure chemical potential is the chemical potential outside the flask. Okay, so this is the driving force for the diffusion. Now, what is the consequence when the pressure builds up inside the solution? Fundamental equation tells us that when pressure change, Gibbs energy change. Assume temperature is constant, pressure increase, so delta G equals V times delta P. If we divide by number of moles on both sides, the molar Gibbs energy becomes chemical potential change. So chemical potential change equals molar volume times pressure change. Since volume is always positive, and this tells us when you increase pressure, gives a chemical potential increase. If the inside the pressure change is pi, then the chemical potential increase will be molar volume times pi. So when can the diffusion stop? Okay, remember initially chemical potential inside flask is smaller than outside. Okay, when the pressure build up and the chemical potential increase, all right, so when this increase of the chemical potential due to the pressure change equals the initial difference, that's when the diffusion stop, because now the chemical potential inside outside are the same. So here is the equation. This is the chemical potential increase due to the pressure, and this is the chemical potential difference initially, okay, when these two are equal, the diffusion will stop. Now XA is the mole fraction of the solvent, which can be written as 1 minus solute. XB is the solute or the impurity. So usually the impurity mole fraction is a very small number because you have a lot of solvent, very small amount of solute. In mathematics and natural log, 1 minus a small number can be approximated by negative XB. Okay, so confirm this by a calculator. For example, use a small number, ln 1 minus 0.01, and you will see this is approximately to negative 0.01. All right. So by this approximation, this equation can be written as molar volume times pi equals RT times XB. Okay. If we divide by molar volume on both sides, then the left side becomes pi. So we have osmotic pressure pi equals RT over Vm times mole fraction of the impurity. So just like the boiling point increase, melting point decrease, osmotic pressure also proportional to the impurity added to the solvent, and this is called colligative property. In the last slide, we derived the equation to calculate osmotic pressure, which is proportional to the concentration of the impurity. The concentration here is a mole fraction, which is number of moles of the solute or the impurity divided by total number of moles. Now, usually the solution is dilute. There's lots of solvent, very small amount of solute or the impurity, and therefore the total number of moles can be approximated by the number of the solvent. So this equation now can be written as RT over molar volume times number of moles of impurity, number of moles of solvent. Combine molar volume and the number of moles of solvent, we have the volume, total volume of the solvent. So we have this equation. The osmotic pressure equals number of moles of the solute or the impurity times RT divided by V of the solvent. Okay. Now this number of moles divided by volume can be written as B, which is the molar concentration or the molarity. Okay, moles of the solute divided by the volume of the solvent. So that's the molarity of the solvent, the solute or the impurity. Now these equations reminds us of another important equation, and that is the ideal gas law. Ideal gas law says PV equals nRT. So pressure can be calculated by nRT divided by V. So in this equation, N is the number of moles of the gas, volume is the number of the gas. Now in Van Hoff equation we just derived, the left side is the osmotic pressure of the solution. On the right side, NB is the number of moles of the impurity, and V is the volume of the solvent. All right. So the comparison of the two equations will help you to remember the equation to calculate the osmotic pressure, the Van Hoff equation. Okay. So in this equation, B is the moles of the solute per liter of the solvent, and that's molarity. There's another equation called molality, is the moles of the solute for kilogram of solvent. That unit, okay, the molality is used for the temperature change, for the melting point change, boiling point change. So in those equations, we use the molality. So here is the molarity, moles per volume. So what can osmotic pressure tell us? The equation tells us that osmotic pressure is proportional to the impurity. Okay, so osmotic pressure is due to the impurity. If you have no impurity, just pure solvent, there's no diffusion, there's no osmotic pressure. So osmotic pressure is a measure of the impurity. Okay, and for example, a 1 molarity solution will has osmotic pressure 22.4 atmosphere. If you use water, that will be 56 feet high. So in other words, the osmotic pressure is very sensitive to the impurity, and therefore we can, if we can measure osmotic pressure, then we can find out the concentration of the impurity. One application of using osmotic pressure is to measure the molecular weights of macromolecules, such as proteins, synthetic polymers. So we start with this equation we just derived. Osmotic pressure equals molar concentration times RT. Okay. Now the molar concentration is moles per volume. Okay. Moles can be calculated by mass divided by molar mass. So grams divided by grams per mole give you number of moles. And then you divide by volume. That is the molar concentration. So here divide by volume. Recombine mass divided by volume, and that is labeled C, is another concentration, but in terms of grams per liter. Okay, M divided by V. Okay, so that's C. So now we have C divided by M. Plug in this equation, so we have osmotic pressure equals concentration C in terms of grams per liter divided by molar mass, all right, times RT. So compare these two equations. One is use molar concentration, number of moles per liter. Here, grams per liter, but we have additional term, that's the molar mass. That's the one we want to calculate. So if we have the concentration in terms of grams per liter, and if we can measure its osmotic pressure, then we can calculate the molar mass. Now in practice, we make a series of concentrations, C1, so concentration different C1, C2, C3, all right, and we measure their corresponding osmotic pressure, so pi 1 and pi 2, pi 3. According to this equation, osmotic pressure concentration are proportional, and the slope should be RT over M. So we connect all the data together and find the slope, a straight line. The slope is RT over M, and from the slope, we can find out the molar mass. For non-ideal solution, this equation needs to be modified. So for those students who are interested, please read the textbook and go over this slide. Osmotic pressure has many applications. For example, it has been used in hospitals, in pharmaceutical industry, and also to monitor the progress of fermentation processes. In summary, we have shown that when impurity is added to a pure solvent, the chemical potential will decrease. And this chemical potential decrease is the driving force for boiling point increase, melting point decrease, and osmotic pressure. And all these properties are proportional to the amount of impurity added. So the boiling point increase is proportional to the molality of the impurity. The freezing point decrease is proportional to the molality of the impurity, and the osmotic pressure is also proportional to the molarity of the impurity in the solution.